All right, so this mini lecture is going to introduce you to the idea of sound. What is sound? And I just can't do it as a trained neuroscientist. I cannot describe the physics of sound with talking a little bit about the physiology because it's just so cool. And the physics and how the physics connects with the physiology. And so we're going to talk in our introduction to sound, and even as we go into the properties of sound that we care about, like loudness and intensity, we'll pull back a little bit of that physiology. So I'm gonna charge you with kind of a question, and it's a philosophical question, but maybe by the end of this conversation you can decide which side of the philosophy you are on. And that is, does a tree make a sound when it falls in the woods, but nobody's there to hear it? All right, so how do we answer that question? How do we answer that question from a physics perspective or maybe from a physiology perspective? So let's first talk a little bit about the physiology. So we process sound in our brain, of course. The auditory system in the brain, it interprets sound based on the inputs it receives, like all physiology. Our brain responds in a way that's based on the inputs that it receives. And our primary auditory cortex, the first area within the cerebral cortex that processes sound, does so based on frequencies. So how quickly, up and down, how frequent, not quickly like velocity, but quickly in terms of frequency, sound enters that system. It interprets different frequencies. And when we hear different frequencies, we interpret them as pitch. So you may have heard that word pitch before. I just want to pull that word out. We're not going to use it in our discussion of physics, but I want you to understand what it means because that's how we talk about it in terms of sound in our auditory system. Pitch is directly related to frequency. The higher the pitch, high voice, I have a high voice, high-pitched voice, or low voice, low-pitched voice, is directly related to frequency. If I increase the frequency of the sound, I increase the pitch. So when you think of something that's high-pitched, like my voice, that has a very high frequency. If I looked at all the frequencies that make up my voice, the majority of them are going to be at a very high value. If I look at a low frequency, the majority of them are going to be at a low value. And you might go back and think about standing waves in our windpipe as that open tube, whether or not the length of that open tube makes sense with some of the pitches that people can produce when they're talking. So think about that in terms of our standing wave discussion. All right. Again, not going to really look into that too much, but I wanted you to at least understand where that word comes from. Now, if there's no auditory system, then do we perceive sound, right? So that gets back to our question at the beginning of the tree. So let's keep that in the back of our mind for that. All right, so we produce these frequencies are interpreted in the brain. That actually means that our brain is tuned to certain frequencies. So if I hit a high pitch frequency, those neurons in my brain get really excited. They say, "Ooh, you're hearing a high pitch." If I hit a low pitch frequency, they get really excited. "Ooh, you're hearing a low pitch." So they're frequency tuned. And if I get a sound that's a blend of frequencies, my voice, for example, has some low frequencies blended in, a whole bunch of sounds being interfered, our brain can actually separate those frequencies out. Well, actually, it's done a little earlier than in our brain. It's actually within our inner ear. So where does sound come in? It comes in this open tube of our ear canal. And it hits a solid structure, an eardrum, and that structure vibrates. And then there's fluid behind that eardrum, and that fluid starts to vibrate, going into our inner ear. Well, back up a little bit. Hits the eardrum, tiny little bones start to vibrate. Those bones hit another membrane, the oval window. Then the fluid starts to vibrate. Got a little ahead of myself. Inside the cochlea, and our hair cells start to vibrate at different places in the cochlea, tuned to different frequencies. So that's where the frequency map starts, in the inner ear. So cool. I really encourage you to go look at all of that. It's a very cool relative to the physics. And it all comes down to the frequencies. So what frequencies are entering our ear dictates what sounds that we hear. But where do those frequencies come from? How is sound actually generated? Well, sound is generated by an airwave. So it's important. Now we're getting into the physics. Thank you for letting me divulge a little bit into the physiology. Sound is actually an airwave. The air itself is moving in a wave-like fashion. We'll talk about how that's generated in just a minute. This wave-like fashion is a specific type of wave. It's not that periodic wave that is transverse, moving the air, the medium, perpendicular to the motion, but instead, sound is a longitudinal wave. It takes a chunk of air and shifts it back and forth so that the wave, the energy travels through the air medium in the same direction that the medium itself is moving. I'm going to represent that in that slinky manner. So we get a compression of the air and then a rarefaction of the air as my sound waves move through the medium. How do they do that? Well, let's imagine we have a little bit of a speaker, right? So here's your box, your big boom, 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 music's coming in, and we have this membrane of a speaker. And as I physically move that membrane, there's little air particles on top of that membrane. As I pull that membrane down very quickly, for example, I pull that membrane down very quickly, leaving a space where there was no air right before that membrane because the membrane was there. And now that air, there's an empty space, a low pressure space because there's little air there. That low pressure, that's my areas of rarefaction. And as I push that membrane back up, as it oscillates with the beat of the music, I push that area back up, then I get a compression of air. My areas of compression as that wave travels through. And these air molecules bump the next air molecules and so on down the line. So I get this pressure wave moving through the air. That is my sound. That pressure wave enters my inner ear, hitting that eardrum, making it oscillate just like the speakers in our speaker system. Okay, so it starts oscillating the bones of my inner ear, oscillating the round window, and so on and so forth down the line. So sound is this air wave, this pressure wave as we move through space. Now, how quickly does this pressure wave move? How quickly can sound get to me? What is the speed of sound moving through the air? Well, thinking back to that wave speed stuff, that has to do with the medium. Well, what medium are we talking about? We're talking about air. So what influences sound, if we're listening to the sound coming through the air, my speaker over in the corner of my room, what influences sound in air? What influences the medium? Well, remember, this is a transfer of energy, so this has to do with the density of the air. It has to do with the temperature of the air, which we know affects the density of the air. So sound travels different in different parts of the world. High up on the mountain is not a lot of difference, but high up on the mountain has a little bit of different density of air, so it's going to travel a little bit different than at sea level. Sound, if it's really hot out, travels slightly different than if it's cold out, again because of the density of those molecules, humid air versus dry air. So it's influenced, of course, only by the medium. But for the most part, we say that sound travels at 343 meters per second, and that's true at 20 degrees Celsius. So about kind of that room temperature. So that's really what we're going to use most of the time. It does fluctuate slightly. It's super fast, right? Fluctuates slightly in different air conditions. So in air. Of course, air is not the only place that we hear sound. Have you ever heard your parents talking in another room and kind of went up and tried to eavesdrop and you kind of listen to the door, but you can't quite hear, so you put your ear flat against the door. You can hear a little bit better. That's because sound also travels through solids. And do you think it travels faster through solids or slower through solids? Think back to that wave speed video that we talked about. It travels faster through solids. More density, those molecules can vibrate really efficiently without too much of loss of energy. And so sound also travels, just like any wave, it travels through different mediums differently. You can hear better if you press your ear up against that solid door. I think in that wave speed video we talked about if you're in the water and you're water skiing and you take a wipe out and you hear that boat in the water and you're like, oh my God, I'm going to get run over. I got to pop up really quick, put my ski up, say I'm okay. And you get up there and you put your ski up and all of a sudden you're like, where's the boat? It's way off in the distance, because the sound traveled so much better through the water than it did in the air when you were up there skiing, or paying attention to the boat anyway, but when you were up there skiing. So again, sound travels differently through different mediums. And this has some practical applications, right? We got to think about how sound travels through buildings or through elements of a building because of construction. Are we in a place where sound is going to influence the construction of various things? The material we use impacted by sound. As an engineer is designing your really fancy earbuds, the material it uses has to be an efficient material for sound to be transmitted through that material that's now sticking in your ear. So, real base introduction of sound. I'm just going to quickly peek at my notes, make sure that I don't have anything about sound that I want to make sure that you know, and then we'll get back to sort of our question of, does a tree make a sound when it falls in the woods? Question. Okay, I didn't say anything in my notes. I do want to do one, before we get back to that question, one quick little practice problem in how we use this information of sound, and something that I think students often talk about and we learn as a kid, and now we can kind of analyze where it comes from. And that is, how do you know how far away a storm is, right? So we see this flash of lightning, we hear the sound a little bit later, and we use that information to determine how far away that storm is. Where does that come from, right? Where's that counting we did as a kid come from? Light travels a heck of a lot faster than 343 meters per second. Sound travels, of course, at 300, we're going to use that as our number, 343 meters per second. So we always see that flash of light, which gets to our eyes much quicker than that sound gets to us. And so we count between the flash and the sound, and that count is important. So if the storm is a mile away, how far apart is that count? Okay, what do you remember from your childhood? Let's test that with our analysis. So we know that speed in general is the distance per time, right? Therefore, if I rearrange this equation, I get my time. My counting is going to be the distance the storm is away divided by how fast that storm is moving, how fast that sound, is moving, the sound of the thunder that I hear. So if my distance is 1,600 meters, which is 1 mile, and my sound travels at 343 meters per second, you might remember this is about 5 seconds. So every 5 seconds is 1 more mile that storm is away. So maybe you remember that from your childhood. It certainly was something we used to think, how far away do I have before I have to get back home before the storm really hits. All right, so back to our question. Does a tree make a sound if no one's around to hear it? Well, if you look at sound from the perspective of physics, absolutely, right? That tree falls. In the process of that falling, it's pushing air out of the way. It's making pressure, a pressure wave, areas of rarefaction, areas of compression, and that pressure wave is absolutely traveling through space. But if you interpret sound as perception, that it has sound is how we perceive a pressure wave, then if nobody's there to hear it, there's no perception of that pressure wave. And then maybe sound isn't made. All right, doesn't sound like, sound like, get it? We really answered that philosophical question, but now you at least have two approaches to it. All right, good job.